So I was given instructions to try to make this elementary, and since Pierre Deligny isn't here, I won't be completely embarrassed during the entire talk. So let me just remind you that in mirror symmetry, what physicists want to do is that they take curve counts, say holomorphic curve counts weighted by area, so sum of e to the minus, let me just write the pairing of the class of some curve u with some symplectic form. Okay, you get expressions of this form. And now if omega varies, symplectic form is omega, let me write class of omega. Omega varies in a family. And you expect that this sort of expression gives you some kind of holomorphic function. That's where periods and things like that show up. But in symplectic topology, kind of when you try to think about these series, the only time we know they converge is, well, a priori, we know they converge is if they're basically finite. So the problem, so these only converge a priori if we have some kind of positivity condition on our symplectic manifold. Positivity. Which implies finiteness of this sum. So, okay, that's slightly unfortunate, but the solution that we hope many of you know is that instead of trying to do this weight with this kind of exponential function, you replace this e by some kind of formal variable. So instead, we use the Novikov ring. Let me really say Novikov field. Okay, so the Novikov field can be defined over different ground rings, but I will just assume that these themselves are complex numbers. That because this is the simplest algebraically closed field that I could think of characteristic 0. Lambda i's are real numbers. Okay, and then when you write a series like this, you basically assume that the limit as I goes to infinity of lambda I is equal to plus infinity. And then we know that when we do Floer theory over the Novikov field, and instead of writing an expression like that, we replace the series by sum of t. Okay, maybe there's going to be some kind of coefficient, but let's not, of minus. You don't put the minus because t is e to the minus. Anyway, the pairing of u with the class of omega. Okay, and now, for example, and this is not exactly what I will talk about, but if you let omega vary in a family, what we expect to get is instead of some kind of holomorphic function in the complex setting, we want to have some kind of analytic function over the Novikov field. So we should get an analytic function. Okay, so that means that we should know.
Is that true?
Well. Yeah, somehow this is linear.
Yes.
So. But that I don't want to say analytic function in omega because omega is going to vary, in kind of real vector space. I mean, really, just want to say you get some kind of series which you can put in some coefficients, and then I'll be more precise. Okay, right now this is kind of the motivation. We want to be able to interpret these kinds of expressions where we see, not just one element of the Novikov ring, but a whole family as some kind of function on a space. Okay, so this is kind of the 5-minute motivation. What I want to do before proceeding is give some kind of references. And of course, the references are going to be on two sides. First, there's going to be references on the rigid analytic side. There is a, there is a wide literature on the subject. Actually, my favorite reference is still Tate's paper. So this paper is called, I think, Rigid Analytic Spaces. For something, a little bit more introductory, there is a paper there's a book by Bosch called Lectures on Formal and Rigid Geometry. Okay. And on the symplectic side, somehow literature is still not what we want it to look like, but hopefully that's just hopefully by the end of this year there will be more things to put here. But probably the thing that I would suggest trying to look at is Fukaya's paper on cyclic symmetry and adic convergence. This is kind of an odd title because somehow there's almost no connection between the cyclic symmetry part and the adic convergence part. But adic convergence. And then my ICM address, which apparently is called, as I checked this morning on the archive, Family Floor Cohomology and Mirror Symmetry. Okay, so let me start with I just want to start with examples. So, so as I said, what we want to do is kind of analytic geometry over this ring instead of kind of complex analytic geometry. So the key idea is to replace the usual Euclidean norm on C by the, let me just call it by the non-Archimedean norm on lambda. What is the non-Archimedean norm on lambda? Well, the norm of a series of this form, some ai e to the lambda I, is equal to e to the minus lambda 0. Okay, where lambda 0 is the leading term. Okay, so the first, if you've never ever seen this, the most confusing thing about this is that t to the 10 million is very small. Okay, that's a very small number in this norm. And t to the minus 10 to the 6 is very big. But okay, so when I was trying to think about how to explain this, I could talk about this norm, but somehow all the symplectic literature is not written in terms of the norm. It's written in terms of just these expressions here, just the exponents here, just in terms of the valuation. By the way, does everyone know what I mean when I say the leading term? I mean the term with the smallest, the smallest lambda I that has non-zero coefficient. Okay. So yeah, I was saying, so this is the norm, but in fact I will talk about the equivalent notion of the valuation. So in this lecture, everything will be expressed. I think this.
So
this
the AI should appear there, not.
the AI, AIs don't show up.
No, don't.
They don't appear.
You're working on So it doesn't matter.
It doesn't matter what this coefficient is. It's only the exponent. Another way to say this is somehow, only the areas of the holomorphic disks matter, not how many there are of a given area when you're trying to figure out the contribution. As long as it's non-zero. That's what leading term means, that the smallest one with non-zero coefficients. Everything will be expressed in terms of evaluation. In terms of, of the valuation of the sum of ai theta to lambda I, and this is just lambda 0. Okay, and as I said, this is what I'm doing because we will regret this, I'm sure, because it makes it difficult to tie to what the literature. But what can I say? Okay, I'll keep this for a moment. I think this is less interesting. So. So as I said, I would like for this to be motivated by examples, so let's do the first example. Now I just would like to talk about the unit disk. Okay, so we know how to think about the unit disk in the complex plane. So it's a set of things of norm 1. So in my language, that's the set of things of valuation greater than or equal to 0. It's really useful to take this. Note, by the way, that the valuation of 0 is plus infinity.
Is it mean to say?
Yes.
Ask you whether this is the closed or the open.
Yes. No. Well. Both. That's the thing. That's what's going to happen. We will. Actually, we won't even do it probably. But Tate introduced a topology, well, let me just say, on the kind of analytic spaces we're going to consider. And with respect to that topology, this disk is both closed and open. Now, it turns out that that topology is not really a topology. It's what is called a Grothendieck topology. But it's, you have to do very delicate things before you notice that it's not really a topology. You basically have to try to take arbitrary unions of open sets before you notice that it's not it somehow satisfies almost everything you could expect, except that something which is, arbitrary unions of opens are opens, but not in this setting. Anyway, so the unit disk. So we'll write with this, greater than or equal to, and indeed, maybe you want to think of it as this closed, but really it's better to think of it as open. I'd like to draw a picture for this. Valuation for z greater than or equal to 0 just means we look at this. Okay, the half infinite interval. Okay. So now we could, really the theory starts by dictating what are the set of analytic functions on D. That's literally what Tate did. So we are going to say that the set of analytic functions on the unit disk are going to be power series in one variable, which converge at every point. So let me write that. So we define the ring of analytic functions on D to be set of, so gamma, let's write gamma D equals series sum ci z to the I equals 0 to infinity, where ci lies in lambda, okay? And this series converges whenever you evaluate it at every point z that lies in D. So which converges, I'll explain in a second, at all z in D. Okay, so just to make a tie with the literature before proceeding further, this is called the Tate algebra. Well, in one variable. what does it mean for something to converge? It means the valuation of ci z to the I, the limit as I goes to plus infinity equals plus infinity, whenever for all z in the unit disk. Okay. But you see, if you take a z in the unit disk, so this expression, okay? This is something I have to check. But if you take z in the unit disk and you try to compute the valuation of ci z to the I, you will find that this is just the same as the valuation of ci plus I times the valuation of z. Okay? But this, by definition, is greater than or equal to 0. So in order for this to go to plus infinity for whatever you put in here, that's just the condition on these. So this is if and only if the limit as I goes to plus infinity of the valuation of ci equals plus infinity. Okay. So, you may see things defined like this, but really it comes from wanting convergence at every point. Now, what I want to say is that if you were doing some kind of Floer-theoretic construction, and and I'm not going to do too much. I don't want to be explicit, at least at this stage. And you do some Floer-theoretic construction, and then you end up with some series of the form, some ci z to the I, where these ci's are somehow the contribution of some holomorphic disk. Actually, the usual way that happens is, let me just do it c to the I. This is some kind of contribution of some holomorphic disk. Okay. Then you wonder, do I get some element of this ring or not? Well, you see, that says that all you have to check that you get an element of that ring, you have to check that the valuation of these things goes to plus infinity. But that usually is Gromov compactness. So Gromov compactness says that there exists only finitely many disks. Well, not quite, but only finitely many in rigid. I'm going to put it in quotes because it's not completely correct. Many disks of bounded area. Okay. But that's exactly the kind of input that you need to conclude that you indeed have an element of this kind of ring.
Yeah, so where z counts like the
For example, z could count the winding number around the boundary. I'm just kind of, yes, indeed. That would be an explicit example, situation where it would happen. You're trying to count where this z is somehow counting the homology class of the boundary of the disk. And this would be the area of the disk, and you'd like to know that this converges, and that's how it would show up. I'm hoping maybe to say things more specifically along these lines on Friday, but I just wanted to say it here. Sorry? Quote means that really it says the moduli space is compact. But now if it's the compact and discrete, then it's finite. That's what it means. If you're counting them, there's only finitely many of them.
Something that was confusing for me for a long time.
Sure.
So this convergence at z, like at all points of t, like 0 is a point of t.
Yes.
So that condition doesn't actually say anything about convergence at 0, and this is the fact that exponents are only positive z to the I actually comes
Sure.
from convergence at 0.
Sure.
So, yeah.
I mean, it's a little bit, so it's almost, but yes, that's a reasonable way to put it. On the other hand, it's also very reasonable to say that functions on the disk should be power series in positive powers of z. You're right. If you put negative powers of z, they should blow up at 0. That's I think, maybe one way to say this. If you allow negative powers, they would blow up at 0. Okay.
Is anybody lost?
Paul insists that this be accessible, so.
Which one?
Umut's comment was simply that, let's assume for a moment that here I would put I goes from minus infinity to plus infinity. Okay? Then, I could compute this and it would be perfectly reasonable. But what would fail is convergence at 0. I would have a problem with convergence at 0. It would blow up at 0. So, at least my interpretation of Umid's comment. Okay. So yeah, so I want to say at least one place where the unit disk appears in symplectic topology. In fact, there's going to be 2 places. So the appearance symplectic. So let's say, let's have X some symplectic manifold, and L inside X Lagrangian, and then we have some kind of J, and everything is regular, and L somehow bounds no J holomorphic disk. Yeah, on this.
The symbol, the sigma I equals 0 to infinity, AI, GI, so does it make sense? Is it a formal symbol, or does it make sense?
Both. Okay. So first, I think of it's a series. Okay. But then when I did this computation, I said, what kind of series am I interested in? Those series such that when I evaluate Z to be a point in the unit disk, that is a point whose valuation is greater than or equal to 0, the resulting infinite series converges. What does it mean for an infinite series to converge? It means that the norms go to 0 as I go to plus infinity, but the norm is e to the minus the valuation, so the valuation has to go to plus infinity. So it really is a function. This gives me a function on the unit disk. Okay? Every point in the unit disk goes to something. However,
I wish we could teach calculus in this range. So this terms going to 0 really does mean that it converges.
Yes, that's the thing. That's the thing that rigid geometry allows you to do. Yeah, is that okay?
What did you want to say after us? However?
Oh yeah, so however, so ideally we would just define this ring to be, some kind of ring of continuous functions on D with respect to topology. That's impossible. Okay. That's impossible unless we do something much deeper related to the work of Berkovich. But we're not going to do that.
Sorry, what is much deeper?
The interpretation of this ring of functions as somehow continuous functions on a space. So, okay, sorry, I don't know what I was here. So kind of some appearance of this. So you take some symplectic manifold, you take some Lagrangian, you take a J, and L bounds in a holomorphic disk. And then we know, and again, that objects of the Fukaya category, that somehow the simple objects of the Fukaya category of X, which are supported on L, should correspond to some kind of what are called bounding cochains. Now, if L bounds in a holomorphic disk, this bounding cochain is just an odd-dimensional cohomology class. An odd-dimensional cohomology class. Okay? But now let's assume that H1 of L equals 0. Sorry, question?
Yeah, what is in quotes there? The what object?
Bounding cochain. The object of the Fukaya. Simple objects. Somehow you could have 2 copies of L, but I don't want that. I want just 1 copy. Things which look like 1 copy of L homologically. So let's assume H1 of L equals 0. In that case, the kinds of bounding cochains that you are allowed are exactly the bounding cochains. So the bounding cochains are elements of H odd of L, okay, which lie in the unit disk. Well, of course, it's actually, this could be higher dimensional, so it could be a product of unit disk in the unit disk. So let me put it like this, with coefficients in lambda, okay, which lie in the unit disk. And okay, so Who is asking the question? Yes, which unit disk? There's only one unit disk.
But what, I mean, so H odd of L, like, is like some Abelian group.
Yeah, but it's okay. There's still only one unit disk. The one unit disk is basically H odd of L with coefficients in lambda as 0. And that's it. Basically, the valuation of A plus B is the maximum of the valuation of A and the valuation of B. So that's kind of, only can use that cube. Okay.
Lambda 0 is D?
Yeah, lambda 0 is D, but I want to think of D as some kind of geometric thing, and lambda 0 is some kind of algebraic thing. So there's some kind of switching back and forth between algebra and geometry here. But let me just say which lie in the unit disk. Let me say specific example. And this is kind of a useful example. The first one that I know that's interesting is L equals S3, sitting inside T star S3. Okay? So you could ask, what is the space of objects of the Fukaya category T star S3 which are supported on the 0 section? Okay? And the answer is that there is a unit disk worth, so in that case, literally H odd of S3 is just a copy of lambda. And inside this copy of lambda, we have a copy of the unit disk. So now I'm going to draw a picture. Here's now a bad picture, but OK. 0. This corresponds to the S3 that everybody likes to think about. OK. And then there are all these other points. Like this point is like S3 with the bounding cochains, which is of the form T to the lambda times the times. OK, now I have to decide what to call it. I usually call it the fundamental class of S3. Okay, where lambda is strictly greater than 0. Well, if it's in the interior, strictly greater than 0. But then you're also allowed ones which are on the boundary, which is somehow S3, which is the fundamental class. Okay, and of course here now you can have some multiple, in your non-zero element of your ground ring K, which in this case is just a complex number. So let me just say an element of the complex number. Maybe I call them, A is complex number. Okay, so the first question you should, when somebody tells you something like this, that somehow if you look at objects of Fukaya category, then you get this constraint and you get the unit disk, you should ask why. Why is it that I cannot put in, S3 with T to the lambda, we're now sorry. That's right. Where now lambda is negative. Why is that not allowed? Yes?
Sorry, I'm confused. Your point in the middle is S3 with no bounding cochain?
Yes, the 0. That's 0. The 0 is the usual S3 that everyone likes to think about. Okay, so why is it that you can't do that? Well, so again, I'm not going to go into the details of this, but I will just say that if I had another Lagrangian, then, and you try to compute, let's say, the Floer cohomology of L prime.
So you need this circle and the point.
Yeah, this is the unit disk.
Okay.
It's a picture of the unit disk. And I'm
That unit disk.
that unit disk. Now, this is another picture of the unit. Yeah.
Okay, that's, yeah.
Yeah. So this is the unit disk where it's been written using the valuation to R, and here it's written using the norm.
And we're kind of pretending that we're in the complex plane.
And we're pretending
just for purpose of drawing pictures, right?
Yes,
There's no
yes.
actual
There's no,
plane there.
no. This is very heuristic. That one is somehow actually accurate to some reasonable extent.
What's an object in Fukaya category for you?
Doesn't matter. What I'm describing.
I mean, apparently you decorate them with.
But yeah, that's what I'm saying. Yes, that's what you should take from this talk. That you should decorate them. So if you do this, yeah. So how would you compute this? Okay. Well, you would compute it in essentially the same way as you compute the one with no B. Okay. Except, so which means you have to count some holomorphic disks.
Does L prime have a B on it?
Doesn't. That's not. Well, that would just make it more complicated. Surely the simplest cases would only L has a B. So let's just do that.
Is L prime without a B the same as L prime with B equals 0?
Sure. Yeah. So this is L prime, and this is L. And clearly, this should be some kind of leading order term of what we're going to do. But then what you do is you represent B as some kind of cycle. Let's just do n sub B inside of L. Okay? And now you count holomorphic disks, which pass through n sub B. And then even more of them. Maybe they pass through n sub B twice. And you notice that somehow, you see the codimension, because here I assume that h1 of L equals 0, the codimension of NB is strictly greater than 1. Okay? So that means that these moduli spaces and these moduli spaces, they're not the same thing. Okay? This one is rigid with no constraint. This one becomes rigid once you impose the condition that it passes through the cycle. So this originally was higher dimensional. Okay? And this one becomes rigid once you impose the condition that it passes twice. So this is even higher dimensional. Okay? So all of these, so you get some infinite sum. Okay? So the key point that I'm trying to make here is that these moduli spaces, they're not the same. You have a different count of moduli spaces appearing. And then what you're trying to prove when you try to show that you can define Floer homology for bounding cochains, in the unit disk, is that because the contribution, when you do something like this, you actually multiply it. There's some kind of contribution that comes from the valuation of B. So this kind of has a contribution.
Are bounding cochains some way of keeping track of unstable disks?
Not unstable. No. It's some way of making higher dimensional moduli spaces of holomorphic disks contribute to your count.
But somehow I should think of them as having some spheres contracted to these points with some
No, don't. Just disks passing through these cycles. Yes, Elsa.
So if B is a class in H of the coefficients in lambda,
Yes.
what do you get from it, an honest cycle?
Yeah, but this is somehow, just imagine that it's,
It's an infinite sum of cycles with powers of t attention.
yeah.
Okay, and the t's will go back into how you count.
That's
how
exactly
you
right. That's
count,
what.
you'll count.
So here there's a contribution of the valuation of B that enters into this expression. And here you get the same contribution that shows up twice. Okay? And so on and so forth. So Gromov compactness tells you that if you were to just count these things, the series that you would get would have valuations that go to plus infinity, but these B's don't make things any worse. That's the point. That things still go to infinity because the contribution of the B's is positive. That's maybe all I will say.
So as long as lambda
Greater than or equal to 0.
This is sort of
Yeah, because the valuation of B is greater than or equal to 0, okay, what you get here is kind of the energy of the disk plus something which is greater than or equal to 0. So it still goes to plus infinity.
Why is the degree of B odd?
Well, if the degree of EB were not odd, then this differential would not be odd. So then you would lose Z grading and the Floer complexes, which is okay. But I'm sorry, the Z mod 2 grading, thank you. You'd lose the Z mod 2 grading, and which is okay, but maybe kind of not something anybody really wants to think about unless they have to. And actually, while we were at it, I should have assumed that L was at least orientable. Thank you. This is somehow.
Is there any more theoretic picture of these higher order terms?
I don't know what.
If the first term is a gradient flow line between two
Yes.
points on a sphere,
Yes.
what are the rest of the terms in this?
Gradient. This is a gradient tree, where one of the inputs of the tree is fed through the cycle B. And this is a gradient. This is kind of trivalent 3, and this is a 4-valent tree where you're moving in moduli. Any Nick?
Why is
Lambda
lambda equals 0 like this?
equals 0. So it's actually it's a slightly non-trivial computation. I mean, yes, I agree with you. If lambda equals 0, then you're slightly worried because here, roughly speaking, because this moduli space and this moduli space are not actually the same. This is some other moduli space. So you can actually control the energy and check that the sum still goes to plus infinity. You see, what does Gromov, let me say it like this. Because Gromov compactness says the moduli space of things of bounded energy is compact. Okay? And now these putting condition B here, condition B squared here, and so on and so forth, cuts that compact things of bounded energy to a zero-dimensional thing at once. And so it's finite. So for all, without using anything about the valuation of B, I can ignore B, I can just think about which moduli spaces I get, the contribution of this below a given energy is finite. Does that help?
Did everybody get that?
It was convoluted the way I explained it. But
Can I sort of wait? What did you say exactly?
let me take a potential confusion. Here's one way you could try to think about it. You could say, let's look at all the moduli spaces of holomorphic disks and let us separate them by virtual dimension. Okay? And let's try to apply Gromov compactness one component at a time, or rather one choice of virtual dimension at a time. And if you did that, you would run into a problem here. If you say, Gromov compactness tells me something about the rigid ones, and Gromov compactness tells me something about the ones which are 2-dimensional, and the ones which are 4-dimensional. Okay? But it doesn't. Gromov compactness tells you about something about all of them at once. It tells you it is a compact moduli space. And then this is the rigid ones. This is the 2-dimensional one cut down to be rigid by some constraints. And so now you have a compact 0-dimensional thing, which you count. Sorry, Paul, you can say something if you'd like.
That entire sum is the cut,
Yes.
sort of a series of cut downs of a single compact moduli space of all possible disks of all index.
Yes.
At any fixed level.
At any fixed level in the energy. Good, that's a very good question, by the way. Yes.
What is NL?
What is what?
NL?
There's no NL. There's NB maybe.
NB?
NB is some cycle in L. I mean, I'm drawing a picture. Of course, this is not how FOQ set up the theory. They don't say choose a geometric cycle, but this is what's happening.
Okay, NB, okay.
Some cycle which represents this class by Poincaré dual to this class. Yes.
So you either drop the associated assumption that H1L is trivial, or
We'll come back to that. I'll come back to it. I mean, yeah.
Is anybody fundamentally confused about this idea of cohomology that's twisted by odd degree classes?
Can you say more about the three-sphere?
Yeah, so, maybe not much more to say about the three-sphere. What can I say about the three-sphere? I'll say something more about the three-sphere later, or maybe if you're interested. I mean, I somehow, the three-sphere is an example. You could do Floer homology of the three-sphere without Lagrangian at T star S3.
But you could write down this series for
Yes.
A non-trivial B.
Yes. You could write down the series from non-trivial B, and you get an object of a chi category.
Now I can't guess what it is.
I'll tell you later, or maybe go back to it at the end. Okay, so.
Can you say what the output of that equation is? What object?
Well, this what I wrote here was the differential that computes the Floer homology between L prime and L twisted by B. Okay, the outcome of this discussion is that if your Lagrangian bounds no holomorphic disk and H1 is 0, then the space of objects for which you can, the space of kind of additional data that you can put on L, so that you can make sense of Floer homology for L equipped with this additional data, that is the space of L comma B's that we're encountering, is the unit disk in H odd.
That's the space of all NBs, is that correct?
That's NBs is just a choice of geometric cycle representing B. So you really should think just a choice of B's. Yeah. Okay. I want to make sure to mention at least one other example of where this unit disk shows up, at least the one-dimensional one, because it's important if you think about SYZ mirror symmetry. So the other example takes place inside. So I like to kind of let me do it heuristically because it will take too long to do kind of explicit description. So there is a notion of a Lagrangian torus fibration with a nodal singularity. So what it looks some kind of fibration over the disk. Now this is this is a base, and then the fibers are generically Lagrangian tori, and at this point here, the fiber is going to be this immersed circle. Immersed sphere, thank you. Okay, and so let's call that immersed sphere L. And if you try to compute HF,
H1 non-zero, is it okay?
sorry, what?
H1 non-zero.
It's absolutely. No, it's a sphere. I'm talking about the sphere.
Okay.
Yeah, HF star of LL, and it turns out that the odd part of this. So the odd part. All I can say is that. So inside of this, there is a one-dimensional vector space spanned by the intersection. Actually, there's actually two-dimensional vector space spanned, but each choice of a branch, but let me just, by a generator corresponding to that intersection. I don't quite know how to separate, to say something convenient to separate. Okay, very good. By one of the two generators. Generators corresponding to the intersection point, whatever. And then, if you would like to understand somehow, so then just like as before, you would like to say, well, can I do L with B? And I equip L with this choice of bounding cochain, which corresponds to that intersection, and make sense of Floer homology. And again, you can do it. You can do it so LB makes sense, assuming the valuation of B is again greater than or equal to 0. This is kind of non-trivial. This is some work of Fukaya. And there's an alternative approach by, I didn't look at the literature, by Zillibach maybe, and Ekholm and others. Let me just mention why there's an issue here. There's an issue here because when you try to put in this bounding cochain, so here we were counting different things, but now when you do this story, so the counts of disks is going to be something like this. First, there's going to be just the disk that passed through L, so L prime and L. Then there's going to be the disk that passed through L prime and L, but with a corner. This is both L and L. This is a corner at B. Okay, maybe this is actually the main thing to say. With a corner at B. And then there's two corners at B. Okay? Now, before, when Nick asked me how do I know that this whole thing converges, I said I can appeal to Gromov compactness for a single thing.
Sorry. Can't the same moduli space contribute? Are we using the fact that codimension is strictly
Yeah.
than one?
Yes.
So that
Here.
moduli space can contribute multiple.
Yes. That's why I started by saying h1 of L equals 0. Okay? But now, if you're in this setting where you're doing immersed Lagrangians, then you have, this moduli space and this moduli space. There is not a single Gromov well, at least you could try to set it up, but at first you can just quote Gromov and say, by Gromov's theorem, this single moduli space is compact, and I just cut it down, blah, blah, blah. So you have to do some additional thing, and what they do, so, both of them use SFT-like ideas, basically. But I don't want to go there too much. I just want to mention that this is an important example.
Is there references for this?
So as I said, there is, so no, Fukaya, there's a 2009 talk that he gave at Berkeley. I think the slides are on his webpage, in his Kyoto webpage. And there is an actual paper by Zillibach and Ekholm. I'll try to, I can find the third author. What they prove, basically, they assume that J is very special in the intersection point, like integrable, and the two Lagrangians are like Rn and R times Rn. And then they prove that it takes a lot of energy in order for you to go back through this, to go through this corner. Or not a lot, a definite amount of energy every single time you go through the corner, and that's what you need to prove these kind of finiteness, this kind of convergence of series.
I think Lapchef is happy with this.
Okay, good. I'm glad I didn't get anybody that wasn't supposed to be on here. Okay. So, as I said, this version is kind of not optimal because it forces J to be standard, but I think it's kind of hopefully can be proved in more generality. Okay, so that was the first toy case, which is just the unit disk. And now, what I want to do is I want to talk about the next class of examples that show up naturally, and they are annuli. So now what I want to do is I want to pick A and B, which are real numbers, okay? And let's say, and then what do I mean? I just mean like make an interval A, B inside R. Sorry. I think I'm going to mess up my. Well, we'll see. And then I want to define the annulus of biradius A and B to be the set of Z, such that the valuation of Z is bounded between A and B. Okay, So the picture here, the picture was that this half infinite interval. Now the picture is that, here is the real line, and then I have the thing between a and b. Okay, so what should functions on the annulus look like? Again, now let's just pretend that we're just going to try to make a guess. Based on the guess from complex analysis, functions on the annulus should be Laurent series. So functions on A are Laurent series.
So let me go back to this.
Yeah.
Is the Lagrangian, is a Immersed Lagrangian, is it Floer homology unobstructed? So
Yeah, so in this case, Floer homology is unobstructed.
have some concrete, have some example of that Immersed Lagrangian.
You mean you want an example of this? Let me tell you later. I mean, you take a K3 surface with standard,
In dimension 2.
Yeah.
What about higher dimension?
Let's higher dimensions are more delicate.
More delicate.
Yes, I will again, depending on time, maybe say something about higher dimensions, but I mean, of course, you could just take a lower dimensional thing, take a product. Yeah. So, but okay. So functions on AB are supposed to be convergent Laurent series. So again, what does that mean? Well, I have a sum of ci z to the I goes from minus infinity to plus infinity, and when I evaluate, such that for all z in this guy here, annulus of biradius a and b, the valuation of the limit as I goes to plus as I goes to both plus and minus infinity of the valuation of ci z to the I equals plus infinity. Okay, great. Now, if you go through this, you just do some basic counting, you'll observe the following thing. If you take a point in the middle, okay, then if you take a point in the middle, then the terms which are negative are going to grow faster at A than they're growing in the middle. And the terms which are, the other way around. So if you take a point in the middle, then the terms which are positive are going to go grow. I always get this wrong. Again, so given any lambda between A and B, the growth of valuation c to the I, z to the I at z such that the valuation of z equals lambda is slower for I negative than so slower for I negative, slower for I negative than ci plus I times A, I times B. This is the wrong thing to write. It's faster. And here I should put an A, and now it's correct.
What Mohammed's trying to say is that if you split the series into two, the
Thank you.
positive I and the negative I, for half you have to test convergence only at the left boundary point.
Thank
for
you.
half you have to test convergence only at the right boundary.
Yes.
What does the first line say? Given and?
Given lambda between A and B, okay? You're trying to test, exactly, you're trying to test whether the series, you're looking at a z with valuation equal to lambda, and you're trying to test this convergence at that point z. Okay? And that splits into two things, plus infinity and minus infinity. As I go, okay. So if you're trying to make sure that this goes to plus infinity, when you plug in z whose valuation is equal to lambda, it suffices to check that this goes to plus infinity, either for lambda equals A or for lambda equals B. Okay? And for one side, you check one side, and for the other side, you check the other side. And so if I got it correct, if I got things correctly in my notes, which is not guaranteed, what you should get is that the condition becomes the limit as I goes to plus infinity of the valuation of ci plus I times A equals to plus infinity, and the limit as I goes to minus infinity of the valuation of ci plus I times b equals to plus infinity. And that looks right. Okay? So this condition here becomes this condition here. Now, I have 15 minutes, so I think I have time to do a little bit of algebra. So what you're actually supposed, so I'm going to do something, and it's going to look unmotivated. So let's define new variables, x1, which is going to be t to the a times z, and x2 equals t to the minus b times z inverse. Good. And now, okay, good. So what you can do is you can think of this series as series. We can think of our ring of functions as series in x1 and x2 mod the relation that x1 times x2 equals t to the a minus b. So that will be useful later. Okay. So now I want to say where this kind of annulus shows up. And there's a special case which shows up all the time. No, I won't. We'll come to it, and then we'll say, oh, look, by magic, that was exactly what we had before. Good. So, yeah, in both directions. So where does this show up? In topology, the case A equals B equals 0, okay, which is allowed. So the case equals B by 0 equals B equals 0 just says that the valuation as I goes to plus or minus infinity of Ci equals 0. The limit, sorry, that's horrible. The limit as I goes to plus or minus infinity of the valuation equals plus infinity. Okay, the limit, in either direction is plus infinity without having to put any of this correction term. Okay. In the case A equals B equals 0 corresponds to bounding cochains in H1 of a Lagrangian. Okay. So what do I mean by that? Well, you could try to do the same thing that I said before. So naively, what you would do is you would say, I have, as before, this is L prime, and this is L, and then I have some cycle, Poincare dual to B, and I add up all, and take this sum. But you see, now, because B comes from H1, this is codimension 1. And the boundary of a holomorphic curve is one-dimensional. So this intersects to this all the time. And it intersects to this twice, generically. There's no, anyway, this does not, these conditions do not cut down the constraints. Okay? So that means that if you try to do the thing we did before, you really do run into some kind of delicate question about how to count these things appropriately. But there is a solution where instead of trying to think about it like this is the naive thing. The sophisticated way to do it, which is, well, this is kind of what FO cube did. And they made this work, okay, by some careful choice of perturbations and things like that. But the naive, the more sophisticated thing to do, which is due to Cho, and then later on implemented by FO cubed, is to just associate to the boundary of a holomorphic, to holomorphic disk, to the boundary of a holomorphic disk, a class in H1 of L with z coefficients. Now, how would you do that? I mean, it's not completely unambiguous, but it's good enough. So let's say you were doing this setting where you have this L prime and L, and you have some intersection points, x and y. Okay. Well, just pick some base point down here in L and some path to x and some path to y. Great. And then concatenate this boundary here with that path. Okay. That'll give you a class in H1. It's not unique, but that's not a problem. The key point is that don't do it one disk at a time. Do some universal choice, and then you'll get so that you get something for all disks. And then instead of doing this infinite count, you're just going to do, you can define the twisted differential to be the pairing, so associated to class B in, now I'm going to write H1 of L with coefficient in lambda star. Okay, to be the pairing, you pair B with the class of the boundary of U times T to the energy of U, which is the thing that we always do. Okay, so now you'd like to sum this over all of U. So now you'd like to know whether this converges. And you can see already, if you put an arbitrary class in H1 with coefficient in lambda star, then a priori in this expression here, you're going to get negative powers of t in general.
Lambda star means non-zero element?
Yes, lambda star means non-zero element. Okay. So the negative powers of u in general. Okay. So we don't want those negative powers of u because we basically somehow in this setting there's just one moduli space of holomorphic disk. We're considering just the rigid ones. We're not putting any constraint like we were doing before. So there needs to be some kind of algebraic reason. We're done doing, algebraic reason for convergence. And the algebraic reason is pretty straightforward.
In case somebody's wondering, so the B on the left of the vertical line and the B on the right of the vertical line
don't live in quite the same space.
are related by the fact that that one is roughly the exponential.
That's right.
Of that one.
So this naive picture.
So when you try to sum this up, you get an exponential series, something that looks like this e to the b involved. So you define u b prime, which is formally e to the b, and then you just have to all this infinite sum here, all these terms here, then become just this one here.
Yes. So here.
You write this as e to the something, and you sum it up, you get back to here, but that one here works better.
Because you don't have to analyze term by term and make sure you understand the growth. And you make sure that these expressions actually give you the expected term in the exponential series. Anyway, yes, indeed. So here B is in H1 of L with coefficients in lambda. And there they're coefficients in lambda star. So this was the naive point of view. OK, so but still, even when you put them in lambda star, you still have this question of does this expression converge or not? And the problem is exactly making sure that you don't have these negative powers. But there is an easy way of making sure you don't have negative. Ooh, I didn't mean to erase this. Oh, well, too late. This is good because I think there's a sign mistake. But if we assume that the value, and I'm going to naively write the valuation of b equals 0, i.e. that b lies in H1 of L with coefficients in what is called u lambda. This is, again, there's this passage between algebra and geometry. So what is u lambda? This is the subgroup of lambda star, which is given by that condition. So valuation of my c equals 0. Okay. So if you assume this, if you assume that b lies in here, then you don't have any problems. Okay. If you look at this expression, what you get is always some. That means that you get something like of the form a plus higher order in t. I'm going to write higher a of u plus higher order times t to the e of u. Okay? So if you try to make sure that some expression like this converges, well, that's fine. You know that e of u goes to plus infinity as you count your holomorphic disks. So that's now, but what is this what is this condition that the valuation of b is equal to 0? That's exactly what I'm sorry, that a and b is the same. That's exactly this condition of being in the annulus. So the conclusion is that the set of bounding cochains in H1 of L, if L bounds no holomorphic disk, is a product of annuli, but a product of annuli of radius 0. Of, well, width 0, I don't know what to call it. Okay? Yes?
In this example, why couldn't the valuation be positive?
Again, there's no such thing, because it's an element of H1. So you could say it's positive on the loops that go positively. But what does it mean that you go positively around the Lagrangian? Yeah. So think of this in terms of monodromy. Okay? There's some local system. Okay? If I have a positive power of lambda, it means if I go around this loop, I multiply by t to the plus lambda. But if I go around the opposite loop, I need to multiply by t to the minus lambda. So it wasn't positive. The only thing that makes sense is this. Yeah, there's an amazing fact that the inverse of a series whose leading order term is 1 also has leading order term, also starts with 1. That's what shows up there. Okay, good. So so that was so that's how these annuli show up. Now, this you cannot kind of keep going on a case-by-case basis. I mean, we can't somehow every single time we encounter some space that looks like it should have a ring of functions, we say, let's try to guess what kind of ring we should be using. Okay? So the general theory so what you do is you introduce something called, I said earlier, it's called the Tate algebra, but this is n-dimensional. So this is let me just write x1, xn. Okay, so what is this? This is kind of formal series in n variables which converge on, so now I should say on the n-dimensional unit ball, but that's the same thing as the product of n disks. Product of n one-dimensional disks and copies of D, i.e., if you plug in, if we evaluate at a collection of numbers xi, such that the valuation of xi is greater than or equal to 0 for all I. Okay, maybe the most important thing is to have a picture for this. And the picture is just the upper quadrant. Okay? So that's the condition on the valuation that we are imposing. And so now there is the definition of what it means to be an affinoid algebra. And an affinoid algebra is just a quotient of this space. Now, of this algebra here. But it turns out that this algebra is Noetherian. So this is kind of a probably. I think this is due to Tate. Tn is Noetherian. And that means that instead of saying that an affinoid algebra is a quotient of this, I can just say that an affinoid algebra is the quotient of Tn by an ideal. And by the above, it's necessarily finitely generated, which is necessarily of the form, I equals the ideal generated by f1 up to some fk. Okay? So you take a collection of functions, and you take the quotient of this by that collection of functions. Now, it's good to have some kind of geometry associated to this algebra. Otherwise, we wouldn't be doing rigid analytic geometry. And the geometric object is called an affinoid domain. is the, well, okay, so algebraically I would say the set of maximal ideals, but it actually is just the zero locus, the affinoid domain associated to such an algebra. So to Tn A is the zero locus in the n-dimensional ball associated of the corresponding idea. And now I just want to do an example. If I take my algebra Tn to be in two variables, and I do the thing that I was doing over there, I take the ideal given by x1, x2 equals t to the lambda, then the corresponding affinoid domain, I can actually draw it like this. If I take valuations, this becomes lambda 1 plus lambda 2 equals lambda, okay? Which means that I get this line. In principle, I get this line, okay? But I only get this line in the unit, in the upper quadrant. So in fact, I only get this interval. Okay? And this interval was the base of that annulus. Okay? So the example that we did earlier, up to probably some sign mistake, I noticed there was some, should have been b minus a. Up to some, anyway, is just an example of taking this two-dimensional thing and cutting down by an ideal. Now, I should stop because my time is up. I think, one of the, what I'll try to do tomorrow, I mean, I'm not going to succeed. There's Friday, thank you. I'm not going to succeed. There's three things I'd like to do. One is I'd like to give an example of an affinoid domain that is not just an annulus or a disk that shows up in symplectic topology. Okay, Paul wants that. The other thing is I could talk about, the other thing I did is we just have these sets of bounding cochains. We say, oh, it looks like the domain, this domain. But really, we should see the ring of functions appearing somewhere. I could make something about the ring of functions, why it shows up in symplectic topology. And the last thing, which is the thing that's hinted to in the abstract, is that this is a local theory. You take a Lagrange and you try to understand things locally, like to glue things together globally. So some subset of those three things will be done on Friday.